We now relate what we know about pressure and depth to Bernoulli's equation. Pressure comes from the fact that if we have a large container of water, let's say a swimming pool with perpendicular sides, a nice rectangular box, we have a bottom area A that's supporting all the weight in the pool. Now if the pool has a depth h and the water has density rho, or it's some other fluid with another density, that's alright too, then the force necessary to support all that water as it's pulled down by gravity is going to be equal to the weight of all the water in the pool. If the bottom has area A, then the volume is A times H. Density rho means that the mass is going to be the density times the volume. And then the force is going to be the mass multiplied by the acceleration of gravity. If we work through the details of this, we see that pressure is the force divided by the area, the force being equal to that of gravity on the contents of the container, and therefore equal to, here's our AH, which is our volume, multiplied by rho, which is our density, multiplied by g, which is the acceleration of gravity. Rho times the volume AH gives us the mass, times the acceleration of gravity gives us the weight of the water, and the force will be equal and opposite to the weight. When we divide the force by the area, we're dividing then this factor by the area A, and we get simply rho GH. So that the pressure on the bottom of the pool is rho GH, if we assume that the pressure is equally distributed, and of course that's what we theoretically predict and what we actually observe. Okay, again, we mentioned down here that F is a total weight, which is rho V times G, which is rho AH times G, and that's what's represented up here. We can obtain the same expression for pressure using Bernoulli's equation. If the pool is full, or the container if it's not a pool, we can compare a point here at the top where the water surface meets the air to a point on the bottom where